Hello everyone, my name is Pietro Verzelli. I'm a PhD student from the Università della Svizzera Italiana, and today I'm going to present my work called Learn to Synchronize, Synchronize to Learn, Measuring the Accuracy Property, which I'm carrying with Cesare Lippi, which is a professor at the Università della Svizzera Italiana, but also at the Politecnico di Milano, and Lorenz, which is a professor at the University of Manitoba and University of Exeter. So what we're going to talk about is discuss the role and the relationships between synchronization and reservoir computing or machine learning in general. And to do so, we're going to introduce synchronization first, then describe what reservoir computing is and their relationships, and then we're going to discuss an experiment. And finally, just a short case about the autonomous case, which is a bit different framework, which maybe has a different theoretical part which we wish to develop in the future. So we start with synchronization. And of course, first we need to introduce the problem, discussing the role of sensitive dependence of initial conditions. Because chaotic systems are characterized by a sensitive dependence of initial conditions. And what do we mean with that? We mean that considering two identical systems, meaning that they have the same update equation F, if they at the starting point, so for time equals 0, they start at the same point, xa 0 equals xb of 0, then they will be the same for all time, meaning that their trajectories will be identical. This is obvious because f, the updating function, is the same. But if the value differ slightly, even a small amount, then the chaotic nature of the system will lead to exponential divergence, right? Because that's the property of chaos, that two trajectories which starts in the nearby, that will diverge. And even if the systems share the same attractor, because of course, again, their update function is the same, the location in time on those attractors, or the attractor because it's the same, will be uncorrelated. And so the problem of synchronization can be stated in the complete synchronization framework, which holds only for identical systems or almost identical. And basically what we want is that the trajectory will converge, meaning that starting from two different positions, for time going to infinity, they will tend to, their distance will tend to 0. And this is basically the framework of complete synchronization, which is the most obvious idea of synchronizing two systems. They start from different points, and after a while, they will be in the same point. And this is, of course, can be stated in this way, where after a transition period, you ask that the trajectory will be identical, or almost identical, at least asymptotically. So some remarks about this. Of course, in order to this to make sense, in order for this discussion to make sense, the total system, the two systems must have the same dimension. So let's call it n. And so what we're actually dealing with is a 2n dimensional system, which is composed of all the a coordinate and all the b coordinate of the two systems. All the coordinate of the two systems together, they form a 2n dimensional space. But the synchronized state represents an n-dimensional manifold, right? Because you have the boundary, the fact that x of a must be equal to x of b. So this is a manifold, a submanifold of the system, and it is invariant, because if the system starts on that manifold, it will stay on that manifold forever, basically. And so what can be studied, and in fact is studied a lot, is the stability of this manifold. So you can define a transverse Lyapunov exponents, which are the equivalent of the Lyapunov exponent, but for this synchronization manifold, and they will determine the stability of the synchronized phase. So if it is stable, it means that if you start close to it, you will be attracted to it, and so the system will tend to synchronize. While if it is unstable, what you find is that if you are even close to it as much as you want, but sooner or later you will diverge from it, and the system will be desynchronized or not synchronized anymore. So an example of this synchronization behavior is the Lorenz system. So I generated two Lorenz systems with the same attractor, with the same update equation meaning the same parameters, and I defined a coupling constant between them. In one case, it's not enough, it's not strong enough to generate synchronization. In the other case, it is. But you see that being the system identical, they live in the same attractor as specified. And so, so they're pretty similar, but the behavior is radically different because in one case they are synchronized and in the other one they're not. The two dots represent the starting point, which are identical as well. But what you can do is that you can plot one coordinate against the other to see whether the synchronization is effective, right? Because, you know, we define the synchronization as the coordinate of one system being equal to the coordinate of the other system. And so in this case, what you got is that in the synchronized case, after a transient, which is I highlighted in blue, the system will tend to the diagonal because that's of course the relationship y of a equals y of b. It was the same for x and z, I just choose a random one. While in the other case, you see that after the transient, this movement doesn't stop. There is no transient actually. They will just keep moving around in the state space with no correlation. And so there is no this simple relationship holding for the coordinate. But so what many people think about is that, okay, but why that this should be defined only by linear or identity relation? Maybe a system which has this shape, so when the coordinates are linked by this complicated relation, as in the right panel, maybe still there is synchronization going on, but we are not able to detect it because we are only looking for identity function, but in reality, maybe there is something else. There is a more complicated function linking the state of the one system to the other system, but we are not looking for it. So that's why generalized synchronization was defined. Actually, it's even more general than what I said because we up until now we've only been studying identical system, and so they have identical trajectories. But the generalized synchronization wished to define a synchronization in some sense that holds for any system. So let's say we have two systems, x and y, with two different update functions, so f and g, depending on each one depending on both of the systems. So basically we have one big system and we are dividing it in two parts, and also the two dimensions are different. So the dimension nx of this first system is different from the dimension of ny of the other one. But can we still define synchronization between these two systems? Does it make sense to talk about synchronized system which do not share the update equation nor the dimensionality? Does it make sense? And the answer is yes, because generalized synchronization can be defined basically generalizing the relationship that we defined before, saying that two systems are in a generalized synchronization if there exists a function, synchronization function, phi, such that y can be written as a function of x. And again, this is just a generalization of the complete synchronization where the function is the identity. So in the complete synchronization scenario, phi must be the identity. In this more general scenario, phi can be any function with some boundaries, but some limitation, of course, but we're not discussing this now. And this will define, again, a new synchronization manifold with a new equation, of course. But phi, in general, could be arbitrarily complex. Can be any function, any shape. And so it's really hard to find the actual phi or even assess its existence, because maybe what seems uncorrelated is actually related by a really complicated phi. But luckily, a really famous paper, in a really famous paper, the authors show that there is a necessary sufficient condition for generalized synchronization, and is based on asymptotical stability. So what is asymptotic stability? It means that a system is said to be asymptotically stable if, when driven by an input, if you take two copies of the system and you let them be driven by the same input, they will converge, meaning that they will be they will coincide after a certain point or tend to coincide. And this is again a necessary and sufficient condition for generalized synchronization. So if you have two systems, you take two copies of one system, one of them, let it be driven by the other. And if the two copies will converge, it means that generalized synchronization holds. And if you are familiar with reservoir computing, this might ring a bell because this resembles the equal state property, right? And that's what we're going to discuss later. But okay, so now let's move to the problem. The reservoir computing. The reservoir computing is a machine learning paradigm used for dynamical system. And the system model we are trying to approximate to learn or study is like that. We have a state system which we do not know, and the source system has its own update equation G. Okay, we have a measurement function U, which is what we are reading for the system, right? It's like an observable of the system, which is through H. While we have Y, which is another observable through K, and which is the target. So our goal would be to reproduce the target without the knowledge of the full state system or full source system, relying only on the measurement of U. So again, we are reading U, and we want to be able to generate Y out of it. So in order to do this by reservoir computing, we need some assumption. The first one is, of course, that we have no knowledge of the system model because we don't need it, and all the paradigm works even without it. And this is a really strong paradigm, right? Because it's not, it doesn't require any knowledge of the system. But what we need is a large collection of measurement of U and of Y, so of the measurement of the target, and they must be available, and because we need big data to compute it. And it must be possible to predict Y from U. Maybe not point by point, but the whole story of U must encode enough information to predict the whole story of Y. That's the assumption we are making. And after a certain point, what will happen is that we will keep having the values of U, but the values of Y will not be accessible anymore. And so we want to learn to being able to keep generating Y also after U is when they're not available anymore, right? So in the machine learning language, in the training phase, we have both U and Y. And in the testing phase, we only have U, and we must be able to generate the correct Ys. So the approach is based on the fact you create a new dynamical system, which we call the reservoir, and you couple it with the input U, and you hope that this will create a representation of your source system S. And then you create you train a readout psi that reads the state of your reservoir and generate the desired output Y. So we divide the training into parts because unfortunately you need to train the system, and the listening you use the U as this notation was into the collegiate listening was in a paper by Ott and other authors. I think Liu maybe is the first one, but okay, there's a famous paper and they use this name listening, which I think is really effective. So because the reservoir is listening to the signal, so you have your signal U, and you couple it with the reservoir, and which is modeled as a discrete time deterministic process. So with the update equation F. So you have this, you generate all of these states of the reservoir time by time, each one driven by an input. And then you fit, you create a readout function, which is able to read each state of the reservoir and generate Y hat, the desired output, trying to approximate Y, the true output. Okay, and you can do this offline, and that's really a strength to reservoir computing because it's an offline learning procedure. But of course, also online learning procedures can be exploited as well, and sometimes they have advantages over it. But we'll only be limiting ourselves to the offline procedures. So again, at first you generate all your state by feeding or the signal into your reservoir, and then you train the system to generate your desired output out of each state. This is getting confusing, so I designed a diagram where we have our system, which is called drive, because in the control literature theory, maybe that's a more common name. So we have our drive, which is a system of interest, S, and we have H, which generates the observation U. So the observation is a function of the system, of course. And this is coupled to the reservoir, which is the response system, right? Because it responds to the stimuli of the drive. And then it's learned to predict y hat, the function, through the function psi. So psi reads the reservoir state R and generates time by time y hat. Y, the true target, the true value of the target is y, which is generated by a function k through the reading the system state S. Okay, I think this is a nice diagram showing what's happening. And so then we need to predict the signal, right? When after a certain point, we won't have any y's anymore, and we need to approximate our y by because we only have u in the, let's call it, predicting phase. So in the predicting phase, you only have u, and you want to generate y hat. And the goal, of course, will be to estimate the function mapping R to y, to true y, assuming that this map exists, and you want to generate the true y's, doing approximation, of course. But what is really important is that the readout function is constant in time. It's not a time-dependent function. It's fixed. So the only dynamical part is the reservoir, which we hope will encode all the dynamics, right? So the dynamics are encoded in the reservoir, and the readout can only read them out. But since U is the same in all the process, because we after a certain point we stop having our Y's, but we still have U. This means that the dynamics will be the same in training and predicting phase, right? They must be the same because nothing has changed for the reservoir, which is just a dynamical system reading an input. And so what we hope is that it's the reservoir that has a consistent representation of the unknown system, S, meaning that it exists some kind of relationship between the reservoir and the true state of the system, which we have no information about apart from the signal U. And we hope that this relation is rich enough to for the readout side to read it and reproduce the desired output. Okay, so all the dynamics are encoded in the reservoir, and we hope that the reservoir is a complex, maybe nonlinear representation of the true state of the system. That's what we hope, because otherwise there is no hope in generating any signal, because the readout is a static function. The readout just read a state and produce the next one. So when is this possible? What do we have some hint of how to do that, of any hope of this working? So Jaeger, in his seminal paper, where basically he invented reservoir computing under the name of echo-state networks, defined echo-state property and suggested that it was needed for the learning to be feasible. So he said, okay, you need this property, which we'll discuss later, but it's pretty famous if you're confident with the literature. And many important results can be proven, assuming the echo-state property. So general approximation of the reservoir of any signal, of the reservoir computing procedure of any signal can be proven if you assume that the reservoir, that the echo-state property holds, or even some encoding of any general attractor or any dynamical system can be encoded if you assume that the echo-state property holds. But proving the echo-state property itself, so saying this system has echo-state property, is really hard in no trivial case. And there are some boundaries, but they are really they're not really effective because they're not wide enough. So for actual echo-state network or reservoir computing, there is no clue on how to understand or know whether a system will have the echo-state property in advance or not. So, but what's the definition of echo-state property? If you, in our context, so under our approximation, it means to require the asymptotic stability of R with regard to its input U. So if you're dealing with dynamical system, deterministic, echo-state property is asymptotic stability of the reservoir with regard to the input. This is what you have. It's exactly the same. If you go check the definition, they would be identical, basically. But this, as we've been saying before, implies the generalized synchronization between the reservoir and the known system S, right? Because the relationship was valid in both senses. So asymptotic stability implies generalized synchronization. So when looking for equistate property, what we are really looking for is this function phi. Sorry, I pronounce it in the Greek way. Phi, which will take which will map the true state of the system unknown into our reservoir, and this function exists and is well posed when the generalized synchronization holds. So again, why is this useful? Because as we've been saying before, the training does not affect the reservoir dynamics in any way. So the training part, only the listening part is dynamical, let's say, and it's not trained. It just go. You generate your reservoir and let it go with the input. But what you're doing in the reservoir, in the training phase, is estimating the static function k, which maps your state, unknown state, to the output, right? So on equation 6, you can see that what you're trying to approximate is y, but which is k of s. But due to the generalized synchronization, r is actually phi of s, because that's what we have been assuming. And so psi of phi of s must be equal to k of s, or at least that's what we're trying to approximate. And k be a time-independent function. This problem results in being a static problem, where one simply has to estimate the function psi, which is k composed with the inverse of phi. The invertibility of phi is a bit complex matter, and we'll discuss it in the paper, which will be coming in a few weeks. But in general, it's not possible to invert this function because the dimensionality of the reservoir is higher than the dimensionality of the system. And so what you hope is that it is invertible, at least locally, in the sense of the inverse function theorem. So all of this might sound puzzling, right? We have a dynamical problem and we transform it in a static problem. So not a time-independent one, but that's actually the strength of the reservoir computing approach. Because at first you create a dynamic representation in an unsupervised way. And then the training part reduces on having just a usually linear regression problem where you just maps all of your state into all of your desired output or desired target, as in my notation. Okay, so now let's deal with experiments trying to show why it is important and what's happening in the reservoir. To do so, at first we need to define a measure of synchronization, and the idea is that using the smoothness of phi. When phi is smooth, the generalized synchronization implies that states that are close in the phase space of the response system corresponds to states that are close in the space of the driving system, right? So this function must map closed state into closed state. So what do? We take what point of the source system S in the driving system, and we seek the closest point in this neighbor, which we call it the time in this T and N, standing for nearest neighbor, D because of the driver. So and so we have this couple of points, this pair of points, and then we hope that the point in the other space R, which is a function of S, will be close to the R, Tn, and D, right? So you have a couple of points, a pair of points in this space, and you see where they're mapped, and find that they should be mapped close if they're close here, because they're mapped by a function phi, which you assume smooth. And so if they are smooth, you can linear approximate it, and so you have and basically the problem reduced in the Jacobian equation 9. Basically, you have this relationship is approximately true, at least linear for small distances, because it's a linear expansion of the system, right? So you are expanding this relation into the linear one. And then you do the same, but this time in the response space. So you find 2 points in the response space, you take them, you take the corresponding point in the drive space, and then you do the same. You have now a different equation, but still the Jacobian is present. It's the same Jacobian because it's computed in the same point. Okay. This is sound a bit puzzling, I think, but actually it's really a pretty obvious idea. And then, due to these two equations, we have two different ways of evaluating this Jacobian, right? One in the driver space and one in the response space. And so we can define the mutual false nearest neighbors as the ratio between the two ways of computing the gradient. I think this notation is helpful because you have all N and D on the driver space, and then R is on the reservoir response space. And so what's the property of this measure? Because if the two systems are synchronized at that time, this measure would be almost 1 or of the order of 1. Otherwise, if they're not synchronized, it would be a really large number given by the size of a tractor square divided by the distance between nearest neighbor square. Okay, so we have a measure that accounts for the synchronization. When it's small, the system is synchronized. When it's large, they're not. And of course, this is valid time by time. So what you do is you take a time average on the whole trajectory of the tractor and see what's happening. So, but how do we construct our reservoir? We implement the Reservoir Computing Network, which is a recent name which I really like. And of course, it's just a network with hyperbolic tangent activation. And we have capital W, which is the reservoir connection matrix, which basically is the linear part of the update. And then W, which is the input vector, which allow the input to enter, let's say, the state. And then, of course, you need some nonlinearity. And we also choose readout function psi, which is in our case linear. So W out will be just our a matrix taking the reservoir state and mapping it into the desired out. And that's what we are training, right? What we want to train is this W out. Sorry. And so what is the task we choose? It's called observer task, where you read only one coordinate. We choose the Lorenz system as a generating system. You only have access to X, the X coordinate, and you need to reproduce Y and Z. Okay, so you need to reproduce the full state of the system by reading only one coordinate of it. And that's what you need to learn. So, for example, here we choose a spectral radius of 1. Spectral radius is, let's say, a control parameter of the nonlinearity of the reservoir. We will not to give you so much details, but larger spectral radius basically means that the reservoir is highly nonlinear, and the small spectral radius means that it's highly linear. And more or less, there are a lot of details on that, but okay, let's skip it for now because it's not the main part of my presentation. And we see that in this case, the MFNN is relatively small, 2.8, and the error, we use the mean squared error to account for how good we are doing, is 0.01, which is definitely small. And so in the top panel, you see the X coordinate, and that's basically what the system always sees. And so it will be going, there's actually no difference between the predicted one and the right one. But the other two, when they become red, it is when the training phase ends, and then it's the prediction. The dotted line, the dashed line is the prediction, while the red one is the true value that it aims to approximate. And you can see that the prediction is basically perfect. Right? There is no clear difference between the two. And it will be going on time. I just take a small amount of small section of the times, but actually I do it for long to compute the mean squared error. But let's see what happens. Let's see what happens if you compute if you choose a small spectral radius. In this case, the synchronization is really, really small, as you can see. I mean, the MFNN is big, meaning that there is a few, the system are not well synchronized. And so the mean squared error is large. Let's say 2 is large enough. You can see that the Y is well reproduced again, but the Z has some problem. If you look at some values, they will not be approximated correctly, and also in the training phase. So this is a problem. The system is not able to grasp all the complexity of the attractor, also in the linear phase. In the training phase, and so of course also in the test it will fail. And if you choose a large spectral radius, a really large one, like 2.8, we see that again, the synchronization phase is 35 in this example, and the mean squared error is huge, is almost 10, 9.1. And we see that in this case, we also fail to predict in the x coordinates. So even if we are seeing the coordinate each time, we fail at reproducing it. There are some phases if you look at the top panel. And while the other two completely fail, also in training, but also in the test phase, of course, and there is the kind of noisy behavior. And this isn't, well, there's a correspondence between the error and the synchronization. So I did a systematic study exploring the spectral radius from 0 to 3, point by point, and plotting in blue the NSE and in red the MFNN. And you see that there is a correspondence between the two. Of course, it's not perfect, it's not linear, but you see that around 1, both when the synchronization is really small, also the error is really small, and then they start growing on both sides in different ways, but they are. And if we fix the spectral radius and use another parameter like the magnitude, this effect remains. It's not as good as it used to be, but still you see that when the input scaling grows, the error grows as well. And so does the MFNN, the synchronization. So actually MFNN measured the non-synchronization. So the larger it is, the less synchronized the system are. And we changed tasks. Let's say we wanted to see how general this result was. And so we tried to use another task where the system was forced to predict 5 steps so the system is still fed with the x coordinate of the system, but now it doesn't have to reproduce y and z, but it has to output x of 5 time steps in front of in time. Okay, so the notation is pretty clear in the top. And you see that, of course, the MFNN is the same because the system driving the U is the same. So the shape of MFNN should be the same, and it is. But this time the error is a bit different because for really small spectral radius, it's still desynchronized, but it's not that much wrong. While growing the spectral radius, it grows and also outgrows the MFNN. Of course, they're different scale. They just a tendency. It's not, those numbers are not comparable directly, as you can see from the different axes. And we tried another system, the Rosler one, which is another pretty famous system, chaotic nonlinear 3D. And we, in the observer task again, we see that there is no big difference. Maybe there's some difference in the behavior, but the problems remain, and the synchronization still. When the synchronization fails, also so does the error. So the possibility of reproducing the attractor is compromised. And okay, the last part I want to discuss really, really shortly, the autonomous case. The autonomous case means it's a different approach and solves a different problem. So basically, in the predicting phase, you stop having your driving signal, and what you need to do is being able to reproduce your own driving signal in a feedback mechanism, right? I hope the diagram is clear. So that's represent the predicting phase of that system, where you just use your own generated output to feed back into your system. And so you create a new predicting system. But the important part is that this is autonomous. So now you have an autonomous system. The drive is absent, is not linked anymore to you. And And this is a really different framework because autonomous systems really have different properties and really different behavior compared to the non-autonomous one. But what some people are doing is that they train the same way the system. So what you do is that you do listening phase is the same, training phase or fitting phase is the same, but then the task is completely different because now the system is autonomous. It needs to go by itself. It doesn't have to. It needs to go by itself. It's not anymore input dynamical system. And so there is a change in the dynamics. You know, I really hope that the message was clear that in the framework that we described before, the training phase and the predicting phase were the same according to the dynamics because U was the same in both states. Here is not. Now U is U hat, is the input you are generating. And so this is a completely different framework. And so maybe the fact that we are using the same training procedure and evaluating it in the same way, generating this readout, which also approximating the signal, and then use it to feed it back, might be ineffective. And in fact, some works show that there are different procedures to be used in this case. They are compared, studied. Hopefully, they will be understood in the future. But lot of progress has been made right now. And this is okay. This is the problem, right? So we are studying a different problem, which is radically different in the same way. And so is synchronization still good to? Is it meaningful to study synchronization in this framework? Well, one note: since we're studying chaotic system, it's not possible anymore to study the mean squared error. I mean, it's not meaningful because, of course, chaotic system, there is sensitive dependence of initial condition. So each small error you make will lead to exponential divergence of your state with respect to the other system. So what you really want to do is you create your system. In this case, we're using only the x coordinate of the Lorenz system. You create your signal, and then you hope that in the predicting phase, the predicted signal will have a similar shape or a similar behavior. This is called climate reproduction sometimes, with respect to the original one. But you can hope that the trajectory will remain nearby, because this is impossible for a chaotic system. You can't remain nearby because every small error you make will diverge exponentially. So what we're going to see now, again, this is just a hint I wanted to give you. It's not, there are some measures to measure whether a tractor is reproduced or not, but I wanted just to show you the problem. So in the top panel, you see with the spectral radius of 1, the synchronization. Of course, the synchronization is measured in the training phase because it doesn't make sense to produce the synchronization between a system and something else that is different, is uncorrelated with the system itself. So I'm measuring the correlation with the training phase and see what it leads to. And so for a spectral radius of 1, the synchronization is small, small enough. And we see that the attractor, the generated signal X, is similar to the signal, to the true signal X, right? I mean, of course, as I said, it will diverge. There is no hope not to do so, but it's a plausible output. Like this seems like it's being generated according to the same ideas. And so, okay, this is fine. But let's see what happens when we have a small spectral radius. Now the MFNN is really, really huge, like 46 or something, but the system is still quite good, right? The prediction seems a nice one. It has this behavior typical of the Lorenz X-coordinate. So maybe it's not a good indicator to study whether the system used to be synchronized in the phase, because you see that even if with asynchronization, the predictions seem to be good, more or less. And same thing, but when we use large spectral radius, we see that MFNN is small, 4, and it used to be 3.5 for a spectral radius of 1, so it's fine. But you see that after a short time, the system will just start oscillating with this nonlinear oscillation, and then it will be will do something weird, but it will stop reproducing the attractor. The system didn't learn the attractor correctly. It didn't. And so the synchronization mode does not encode this. It's not able to grasp this fact that even if the synchronization was fine in the training phase, it leads to some problem in the test phase. Because of course, we've been studying the system as if it was a non-autonomous input-driven system, but now it's not anymore. Now it is an autonomous system. And so maybe studying with the framework which was created to study the input-driven system is not a good choice. But again, this is just a hint I wanted to give you. It will be the idea for my future research, but I think it's really important to understand this difference, that autonomous systems are different from input-driven systems. And so we can go at the conclusion. So, okay, when training a reservoir computing network, we want the echo-state property to hold because it can guarantee a reliable computation. It was found by Jaeger and was confirmed by a lot of experiments later. There are some, actually recently some objection were reason. So to this concept of echo-state property, maybe it's not needed, maybe it's not as good as it used to be, but still, in a general sense, maybe ESP is what you want in general, or something similar to it is what you want. But the echo-state property is analogous to the asymptotic stability of the reservoir computing with regard to its driving signal U. Okay, this was what we've been discussing. So they're the same. And the asymptotic stability implies, and this implied by, of course, but what is important is it implies the generalized synchronization between the reservoir computing network and the source system generating the input. Okay, so this is what is important, that the echo-state property that was defined by Jaeger actually is the generalized synchronization. That's what you're asking for. You ask that there is that the system that you can observe, the source system, and your reservoir are synchronized. And because under this assumption, under the general synchronization, the learning problem reducing finding a static mapping. And you are guaranteed that this map exists. And if you are, and you can hope to approximate it or finding it in some sense. And you can use it, of course, to generate the desired input in this context. And we can quantify this general synchronization in a nice way using this mutual false nearest neighbor, which is something developed in the 90s in the dynamical system community, which is a nice way. And we show that it's a good proxy for the generalized synchronization. And we show that this is also a good proxy for the error that your system is making, meaning that when synchronization occurs, the prediction is fine. And so the learning process can be defined as successful. And in the last slide, I discussed how this wall approach maybe is not well posed when the reservoir is using a generative scenario, so with feedback. And maybe the generalized synchronization might not be a good measure of the performance in that case. So we can use the generalized synchronization to study what's happened, because the system is a different one, and the assumption that you are making, they are different, and maybe generalized synchronization is not the right perspective to study. And again, since the generalized synchronization is the echo-state property, maybe the echo-state property is not what you're looking for in that scenario. Okay, I concluded. Thank you for the attention. Hope this is helpful. And the paper should be coming in a few weeks. So hope that it will interest you and you will read it. Now I will just go to this slide with the bibliography so that you can see what paper I was mentioning beforehand. And you can stop the video and look for them. Okay, thank you for the attention. And I'm waiting to see your presentations.